Welcome back. So that's a very challenging system. I'm sure your list is even longer than mine associated with how would we make that happen? Well, hopefully you saw the temperature difference, even to achieve that very marginal efficiency, was at 2,000 meters below sea level. So you have huge pressures, static pressures associated with that. You would have to reach those temperatures and to reach those depths, you have to go pretty far offshore. And so any sort of offshore technology requires these long transmission distances, and that's an inefficiency when you're trying to bring the power back to shore. The deep ocean depths require not just large and expensive equipment to set the systems up, so for you to anchor the system to the floor, things like that, but they also require large and expensive equipment to operate continuously. Of course, the salinity of the ocean is pretty caustic on most pieces of equipment, and as a consequence, you end up having to use some pretty expensive materials in order to have something that's durable. And those are just a few, and some others are listed here. But it's a challenge to try and extract the energy from these systems, primarily because of the depths and the environment that you have. So often we look at these types of technologies, and we'll look at these more and more as we develop our skills and tool set to analyze them, is we find scale is what really affects us. So in order for us to have a high power generation, we have to go to these very deep, sea levels to get the low temperatures. And then in order for us to have significant power from the systems, we need to move a lot of fluid around. So scale often is the biggest challenge associated with power generation. Okay, so let's get back to discussing the Carnot cycle. So recall last time we talked about the Carnot cycle. Again, I'm going to go ahead and draw our little schematic again. So we have T high and T low, and we have our system in the middle. And again, we're generating power out of the cycle. And again, we do that because it's a heat engine, and we can supply heat from a high temperature, and we can reject heat at a low temperature. And we're going to have this discussion. There's a pretty extensive discussion we're going to have about the Carnot cycle right now, only in terms of the power cycle. And we can do the exact same thing for the refrigeration or the heat pump cycle. Again, we just need to reverse the energy transfers. So we're only going to discuss power for right now, but understand it's very easy for us to extrapolate this to the refrigeration and heat pump cycles. So now remember, we talked about for the Carnot, efficiency for a power cycle is the maximum efficiency we can ever achieve, and we saw that that was given by this expression where we had the ratio of the temperatures. And we saw how that was parallel to the definition for the efficiency for a power cycle for any arbitrary power cycle, where we have the work for the cycle divided by the heat transfer for the cycle. Now we're going to pause for a moment and recall, I just want you to have these in your notes and available to you, that if we have a refrigeration cycle, remember we defined beta as a coefficient of performance. And that was, again, what we wanted, which was the heat transfer out of the cold or low temperature reservoir. I'll call this cold so it's very clear. So it'd be the same thing as, it would be the same labeling associated with low temperature reservoir, but remember it's going in the opposite direction for a refrigerator, divided by what we paid for to get it, which is this work transfer for the cycle. So the maximum coefficient of performance that I can achieve is that described by the Carnot cycle. So just like before, we had this parallel structure for temperature and this general description of the performance of the power cycle, we can come back here and do the exact same substitution, where we have the low temperature associated with the low temperature or cold reservoir. We have the net work transfer for the cycle, and remember, that's simply given by the net heat transfer for the cycle, which is the difference between the two temperatures. So that's T high minus T low. Remember, we're kind of throwing away our sign convention right now, just so that we have everything to be, just so our results are positive. Also remember that these temperatures all have to be on an absolute scale. So we have to use either Kelvin or Rankine when we calculate these coefficients of performance. Now this was for the refrigerator. Our heat pump, remember, looks a lot like the definition for the refrigerator. The only difference being is that we're now trying to reject heat using the high temperature source, and so that's going to be Q high divided by the network transfer for the cycle. And again, for Carnot is going to define the maximum coefficient of performance for the heat pump. So that's again a gamma Carnot, and that's simply given by the appropriate temperatures in the system. Okay, so again, maximum cycle performance is always defined by the Carnot cycle performance. Okay, all right, and again, we're only going to consider the power cycle from here on out, and we can then map that to the refrigeration and the heat pump cycle. Pretty straightforward. Okay, what is the Carnot cycle exactly? Well, remember, our cycles have to start where they end, so we know that the final state is equal to the initial state. And the Carnot cycle is very strictly defined in terms of the process steps. Okay, so there are 4 processes associated with the Carnot cycle. It consists of 4 ideal processes. And that's how we get the maximum performance out of the system, because they're all ideal steps. They're ideal. They're also reversible. That's tied to the second law. That's a definition for the Carnot cycle, but it's one that we don't have the tools to use when we talk about reversible processes, because that's a second law analysis. Okay, so the Carnot cycle is defined as having 1 adiabatic process, 1 isothermal, and then a second, so let's call this the first adiabatic, and then the first isothermal, followed by the second adiabatic process, and the second isothermal process. So we know that if a process is adiabatic, that the heat transfer is 0. And we'll go ahead and label these from 1 to 2, from 2 to 3, from 3 to 4, and then from 4 to 1. So these are the states. So it's 4 ideal processes connecting 4 states. Connecting 4 thermodynamic states. Okay, so from 1 to 2, the system is adiabatic. From 2 to 3, the system is isothermal. From 3 to 4, the system is adiabatic. And from 4 to 1, the system is isothermal. Okay. Now, what we're going to do, so here are the process steps. So now what I'm going to do is link these processes to components. And we have 2 systems that we use to represent power cycles. We either use a system where the working fluid undergoes phase change, or we have a working fluid which is all in one phase, gas phase. Okay, so we'll go through and show you how the Carnot cycle maps to the phase change system first, and then we'll discuss the single phase system. Okay, so again, phase change first. So again, we're going to try and bring our system a little bit closer to reality. So we're going to have our high temperature reservoir, and this is going to be my coal-fired burner, my nuclear core, my solar heater, so anything that creates my high temperature reservoir. And I'm going to take that heat transfer and I'm going to direct it into a boiler. And my working fluid is going to be water, so boiler, as the name implies, is going to boil the water from a liquid phase to a gas phase. And then I'm going to take that gas phase water and I'm going to expand it through my turbine. So this is my turbine. And we'll give you a direction here. And then after I've extracted all that good energy out of my turbine, so that's my work out, we'll call that work for the turbine, that's a little t. That's a heat transfer, okay. After I've extracted all that high quality energy from the steam out of the turbine, I'm going to then condense the water back to a liquid state through a condenser. And then I'm going to increase the energy to close the loop to make sure that I have, in fact, a closed cycle system. I'm going to increase the energy of the water by pumping it from a low pressure out of the condenser to a high pressure into the boiler. So this is going to be my work into my pump. And here, I'm going to reject heat transfer out to my low temperature reservoir, and that's here. And all power plants that operate as a heat engine have to operate within this generic setup, which means all power plants have to have a way to reject heat transfer to some low temperature reservoir. Okay, so before, when we had our generic system, this is what was in the black box, okay? A boiler, a turbine, a condenser, and pump. And this is the most generic components. In reality, power plants are a lot more complicated than this, than what's shown in this figure. And we'll start talking about the degrees of complexity that we introduce primarily to improve the performance and efficiency out of the power plants as we move forward from this basics. We start with the basics, and then we'll show how we can improve that pretty quickly. Okay, these are the process components. Let's go back to looking at our pressure volume diagram, and we can see where the phase change exactly fits on this system. In general, we talked about heat exchangers, and heat exchangers, if they're ideal, if they're behaving well, there's no change in the pressure across these heat exchangers. So let me go ahead and label these, give ourselves some states here. So we'll call the entrance to the turbine state 1, exit of the turbine state 2, exit of the condenser state 3, and exit of the pump state 4, and that's also the entrance to the boiler. So we go ahead and we put our saturation region, our dome, on the PV diagram, and then we need to go ahead and put some isothermal lines on here. Okay. Okay. Now, let's start with the exit of the boiler. Let's, again, start with the most basic system where we say, well, we're just going to boil the water just to the state of being a saturated vapor. So we know that that takes us to a quality of 1, which means that this exit state 1 is at the high pressure, because we know we want high pressure is associated with high temperature. We want high energy or high temperature at the entrance to the turbine. So this, sorry, I should have labeled it like this. So we know that this pressure line is the pressure line associated with the boiler. So the high pressure line here, and this is the low pressure line associated with the condenser here. As you go through and do more and more sophisticated analysis for power plants, I can give you a hint that every time you see a heat exchanger, if we're going to treat the system as ideal, then we introduce one pressure for each heat exchanger. So when you go to draw your pressure volume diagrams, you see this boiler, which is a heat exchanger. You see this condenser, that's a heat exchanger. And you say, this system has only 2 pressures that I need to consider. Okay, so we've anchored state 1. As we expand the fluid through the turbine, we need to connect between this higher pressure here, we're going to call that P high, and this lower pressure here. So we're going to drop to this lower pressure. The shape of this line is what's defined by the second law. Or if we don't want to invoke the second law, which is what we'll do in this class, we'll go ahead and we will, in fact, I'll give you an efficiency, and that will dictate what this process looks like. But it's always going to move in this direction, again, because of constraints of the second law. It'll always move to the right. Okay, and then we go and we're going to condense the liquid in the condenser, and we'll just take some arbitrary location here to exit state 3, somewhere along the same pressure line, but not quite to a fully saturated liquid. And then we're going to go up to the entrance of the boiler, which we're going to assume is, in fact, a fully saturated liquid. Okay, so saturated, this has a saturation of 100%, and this, or quality of 100%, and this state 4 has a saturation quality of 0. Okay. And we'll draw some arrows that tell us that's the direction of the power cycle. So again, these are the basic components that can be used to describe a Carnot cycle. Remember, we said that the Carnot cycle consists of 2 isothermal steps and 2 adiabatic steps. So here's my isothermal step from 4 to 1. This is an adiabatic step from 1 to 2. From 2 to 3, that's isothermal. From 3 to 4, that's adiabatic. Now, what we don't have is a tool to put adiabatic, that statement, together with isentropic. And that's a key piece of information. We're going to take that information and we will be able to show how the process looks on temperature entropy diagrams, but again, we're not going to calculate the state conditions. So we'll show you how to use that information, at least in a qualitative way. Okay, now this was for the process components for working fluid with phase change. Now we want to consider what would the process look like if we have working fluid that doesn't undergo phase change. So for example, air. That's our good example for a power plant that operates using a working fluid that doesn't have phase change. So again, we'll set up our high temperature and our low temperature reservoir. And now what we're going to do is connect these to your average, your typical reciprocating engine. So we're going to draw, these are little piston cylinders that I'm going to draw here that are going to represent the process steps. So we're going to take heat and we're going to direct that into the air in a piston cylinder. So this is isothermal heat addition. After that process is complete, so that's isothermal heat addition, I'm going to take that working fluid and I'm going to expand it adiabatically. So this is isothermal heat addition, and this is adiabatic expansion of my piston. And then I'm going to have isothermal heat rejection, and then again to close the cycle, and we'll label these the same way we had before. So 1, 2, 3, and then this will be 4. We follow that by adiabatic compression. So we have adiabatic expansion, and its complement is going to be adiabatic compression. Okay. We know adiabatic expansion. By now, I hope we know that this is a work-out process. So that's work-out. And we know that adiabatic compression requires work in. So we have all of our energy transfers correctly labeled here. We have the heat transfers and the work transfers. And it has, again, exact parallel structure to what we had with the phase change fluid, except now we're just considering a single phase. And that means when we go to look at the pressure vapor diagram that corresponds to these 4 steps, to these 4 process paths, that in this case, you know, our dome would be way down here. Let's say our working fluid is air. And so, not to scale, of course. Let's see if I can draw these. Like this. So here's state 1, and we have this adiabatic expansion process. So the volume expands from 1 to 2. I probably should have drawn this curve with a steeper gradient. From 2 to 3, we have this isothermal heat rejection. So that's 2 to 3. Followed by, from 3 to 4, the adiabatic compression process. Again, to complete the loop, we have this isothermal heat addition. And this would be what's representative of what goes on in your engine in the ideal case. So this is, again, ideal. So we have the basic components. We can see now how the process steps link to actual components, actual devices that we see in the world around us. Our next step is to try and actually do some analysis for these systems, actually take each process and consider the conservation of energy and the conservation of mass, if it's necessary, if we have an open system. And let's evaluate the overall thermodynamic efficiency of these power plants. So what I want you to think about before you come back next time is what power plant will have a higher theoretical efficiency? A power plant that uses water, which undergoes phase change, or a power plant that uses air? We'll talk about that next time.